Yes.
Thank you very much. Let's get started. Good morning, everyone. I'm Zhang, and I'm a PhD candidate at the University of Michigan. So today I'm going to present our work, Next Step Attention, for sequential pedestrian trajectory prediction. And this work is sponsored by the Denzel International America. As I noted also, the autonomous vehicles need to predict future trajectories of its surrounding pedestrians to plan their motion accordingly in order to avoid accidents. But at the same time, long horizon pedestrian trajectory prediction is still a very challenging problem in this field. So current work has some limitations. Some work are only able to conduct short horizon trajectory prediction, like 2 to 3 seconds into the future, while some other work focusing on manipulating model architectures, especially those deep learning based methodologies, to learn factors affecting working behavior. However, such factors can be numerous, and it would be hard to include them all in the model, and that can actually also increase the computation cost. So in this work, we propose a deep learning model called Step Attention to conduct long look-ahead pedestrian trajectory prediction. And this figure shows the proposed model architecture. It contains 3 main kernels. First of all, we have a LSTM RM kernel, and then a time distributed kernel in the middle. And lastly, we have a GRU RM kernel. So the mechanism is that given a history sequence with pedestrian trajectory history sequence with m time steps. So the m means that we look m time steps back, like the history length is m. So first of all, an LSTM kernel is constructed to learn time-related high-dimensional features. And in this LSTM kernel, we have 2 LSTM layers, and it's a simple encoder at the beginning. And then we have a time distributed kernel established in the middle to further learn patterns inside each time step. During the process, within this time distributed kernel, we mainly use convolutional neural networks or CNNs, and also augmented attention mechanism to learn the global information, because CNNs are only able to learn local information. And inside this time distributed kernel, we then have some fully connected layers at the end of it. And then lastly, we use GRU-based RNN kernel to learn and decode the position of the next time step. And then we use a sequential way to predict a full future trajectory. Note that in this architecture, we use a history sequence to predict the position of the next time step, not a sequence. To generate a full future trajectory or predict the full future trajectory, we use a sequential way to do the prediction. The model outputs n predictions through n executions. As we illustrate here, given a history trajectory buffer in the first execution, the model predicts the position of the next time step. Then the model removes the oldest points in the history buffer, and then we pushes the predicted position previously into this buffer, and then we generate a new input buffer, and then that buffer gonna be used to predict the position of the next time step. And by doing this repeatedly, we can get a full predicted trajectory. And we conduct experiments on public benchmark dataset and evaluate result in terms of 2 metrics. First of all, is the average displacement error, or ADE, which is the average error of all predicted time steps. And then also final displacement error, or in short FDE. And this is the average error of all final predicted time steps. And the result values are shown in the table on the right. So we use the benchmark dataset called CheckNet, and the CheckNet dataset has 20 sub dataset inside it. So we conduct the experiments on this 20 sub dataset compared to the compared to 3 benchmark methods, including social LSTM, social GAN, and occupancy LSTM, which were state-of-the-art benchmark method in the literature when this work was done. And we show that we show the result in the format of ADE/FDE. The best performance of each sub data set is highlighted in blue. So as we can see from this detailed table, we show that the model outperforms benchmark method. In detail, that we can see that among all sub data set in this benchmark data set, the proposed model overwhelmingly outperforms state-of-the-art benchmark methods. And the overall performance of the model is shown on the left table. So the general performance for the model is that the ADE is 0.53 meters, and the FDE is 1.72 meters for predicting future 4.8 seconds pedestrian trajectory. And we also investigated real-world performance of the model in both Dublin, Ohio, and also in Ann Arbor, Michigan. The figure shows the displacement error propagation trend along the prediction horizon. And we show that the model achieved promising performance when predicting future 5-second pedestrian trajectories. So according to the figure, we see a near linear error propagation trend along the prediction horizon. And for Dublin case, the ADE, FDE are 0.74 meters and 1.4 meters. And for the Ann Arbor case, the ADE, FDE are 0.76 meters and 1.7 meters. So for all experiments, including the benchmark case and also this real-world intersection case, the ADEs are within one steplet of an adult, which is about 0.7 meters to 1.5 meters. So in this slide, we show some cases of the model performance regarding different walking behavior. And the model shows accurate prediction in real world for different walking behaviors on different surfaces, such as walking straight, walking curvy pattern, turning on both sidewalks, and also the crosswalk. The top left figure shows the predicted trajectory when the pedestrian. So yeah, by the way, so in this figure, the blue dots means the training segment, which is the history trajectory, and the green dots are the ground truths, and the red dots are those predicted trajectory. So the top left figure shows the case that the shows the predicted trajectory when the pedestrian is when the trajectory is stopped at the intersection, and our model accurately predicted the future trajectory, which consists of the pedestrian not moving. And the top middle figure demonstrates the model performance of a randomly selected pedestrian walks straight on the sidewalk towards the intersection. And here the corresponding ADE is 0.22 meters for a 6-second long prediction horizon. And the top right figure, here we show the instance of walking on the crosswalk, and the corresponding ADE is 0.5 meters. And the bottom left figure shows the model performance of the on the case where the pedestrian walks in the curvy pattern on the sidewalk. And the model accurately predicts the future 6-second long trajectory with an ADE of 0.29 meters. And the rest two figures illustrate the performance of the model on predicting turning behaviors. So in the bottom middle figure, the pedestrian walks on the crosswalk, but turns left onto the sidewalk. The step attention model accurately predicts this behavior, and with a corresponding ADE of 0.49 meters. And in the bottom right figure, the pedestrian is walking on the sidewalk towards the intersection, and it makes a turn to continue walking on the sidewalk rather than cross the intersection. And as demonstrated, the stable attention model successfully predicts this behavior, and it has an ADE of 0.30 meters. So a short summary is that in this work, we propose a deep learning model called stable attention for long look ahead pedestrian trajectory prediction. And the proposed model outperforms existing state-of-the-art benchmark methods in terms of average displacement error and final displacement error, which are 0.53 meters and 1.72 meters. The proposed model gains excellent performance in real-world experiments and obtained a small ADE and FD for 6-second trajectory prediction. And the ADE result are within one step length on both benchmark dataset and also the real-world intersection dataset. And we also demonstrate that the near-linear error propagation trend can be obtained with the proposed model. Thank you, and I'm happy to answer any questions.
Thank you so much, Ethan. Very interesting work. We have a question from the chat. Luis is asking, how was the data on pedestrian trajectories gathered? Can you explain?
Yeah, sure. So for the benchmark dataset, as a public benchmark dataset, so we just use that as just like any others. But for the real world dataset, it can be a little bit more complicated. So for the so remember we have two experiments. One is for Dublin, Ohio. That one is gathered from the sensors that we deploy on the deploy in the intersection. We have a connected vehicle testament connected vehicle test corridor there, and we use those RS2 sensors to capture those vehicles, pedestrians, and this kind of information. And then we extract those pedestrian trajectories inside that. And for the Ann Arbor case, the Ann Arbor case is corrected based on the cell phone. So we use cell phone to to correct those GPS information. So so it can be a little bit different than the Dublin case. Yeah.
Thank you so much.
Thank you.
Anyone else want to ask any other question to Ethan? Feel free to do so. If not, then we'll continue with the next presentation, which is micromobility implementation challenges and opportunities, analysis of e-scooter parking and high-use corridors with Myriam Zakhem from the Southern Methodist University. Myriam.
Hi, everyone. So let me share my screen. I cannot share my screen. Could you allow me?
Yes, let me see. Should become co-host soon. Yeah. So should work now?
I cannot share my screen.
One second. Okay, can you try now?
Yes, it works.
Okay, perfect. Please introduce yourself and continue.
Are you able to see my screen?
Yes, perfect.
So hello everyone, I am Myriam Zakhem. I am a PhD student in civil engineering and a research assistant for Dr. Janille Smith-Colin at Southern Methodist University. So today I will be presenting my work entitled Micromobility Implementation Challenges and Opportunity Analysis of E-Scooter Parking and High-Use Corridors. So first, let me present, this presentation is organized as follows. So first, I will have a brief introduction on micromobility services, and then a big background about these shared micromobility services and the challenges faced by city after the introduction of these services. And then I will present the research contribution, the case study application and the data used, and the descriptive statistics are also provided. I will present the methods developed for in this paper, and I will show the results and solution, and then we will have a brief summary of the work. So, shared micromobility systems, notably e-scooter, have grown in popularities in cities worldwide. The rapid rise of shared micromobility systems poses major challenges for cities, prompting some to prohibit the use of these services within their jurisdiction. Given the rapid growth of micromobility industry, cities continue to seek strategies to support micromobility technology implementation. Thus, this research presents a roadmap for dockless shared micromobility vehicle data analysis, including a suite of tools necessary for the successful deployment, integration, and management of micromobility services. So micromobility usage has grown significantly in the United States over the last few years, as 48% of all trips are less than 3 miles. As shared micromobility services have grown rapidly and almost without any warning, there were few studies about micromobility services. As such, cities and DOTs have struggled to manage these services. The challenges associated with the introduction of these services were related to parking practices causing clutter issues and parking blocking, and driving behavior causing safety issues. This paper tackled parking and infrastructure challenges by offering 2 techniques for analyzing area of high parking demand and high-use roadway segments. These analysis processes are applied to data sets consisting of tens of thousands of e-scooter trips completed in Dallas, Texas. This paper contributes to the literature by presenting methods to enhance the effectiveness of dockless vehicle services and address problems created by these services and achieve better implementation performance. Additionally, the paper presents a detailed comparison of common methods used in high-use streets identification. First, let's start with presenting the case study application. So the city of Dallas introduced dockless shared micromobility vehicles in June 2018. Following 2 years of successful dockless vehicle program, e-scooters were removed from Dallas streets on September 4, 2020. Efficient, effective, data-driven management of micromobility services is a priority for the safe introduction of these services within cities, as well as the ongoing management of these services. The city of Dallas here is taken as a case study. The proposed techniques are applied to datasets provided by 2 sit-down e-scooters vendors that were operating in the city of Dallas, Texas. So first, we started by inspecting the data by exploring the descriptive statistics. The descriptive statistic for the 2 key performance measures, the trip duration and trip distances, are presented in table number 1. Next, the temporal trip pattern were examined to give an overall image of e-scooter use by day of the week and time of the day. For example, the average of e-scooter sit-down e-scooter trip per day on the weekend are higher than the average of the trip during the weekdays. Then we perform a spatial analysis by identifying the spatial distribution of origins and destination. These points were intersected with census block layer in ArcGIS. The darker the zone color, the higher the number of origin and destination in a zone. Then the top 50 high-use zones are identified. The three main areas are identified as having high e-scooter use. We have the downtown area, the uptown, and the entertainment district. So the methodology implemented in this paper addresses two identified micromobility challenges: the parking practices and the infrastructure improvement. So first, we developed a parking allocation method using the density-based special clustering of application with noise, or also known as DB-scan, to identify areas of parking need, to identify best location for parking, and to support parking enforcement. On the other hand, we also developed methods to identify high-use streets, to identify location for infrastructure improvements, and to identify location for ordinance enforcement. All these methods will be elaborated more in the next slides. So first, let's start by the parking allocation method. A trip clustering method is suggested to identify parking zones for dockless e-scooters. First, this method clusters the origin and destination points of all the trips in the dataset using the DB-scan and ArcGIS in order to identify the candidate parking sites. In addition to examining candidate parking site, morning launch site, or location at which e-scooter were positioned or launched in the early AM hours of the day were analyzed. The launch site can be deduced by clustering the origin of morning e-scooter trips extracted from the dataset provided by each vendor. The launch site analysis of each vendor was performed to ensure that parking infrastructure is installed at each vendor's location site. The clusters were classified based on the parking demand level. Parking demand level was determined by examining the number of e-scooters parked at a cluster site per day. We identified three levels: the low, medium, and high e-scooter parking demand level. The threshold for the low, medium, and high e-scooter parking demand level were 1 e-scooter per day for the low, 2 to 3 e-scooters per day for the medium, and 4 and more e-scooters per day for the high. Finally, all parking zones were designated to were designed to mitigate the sidewalk blocking. For example, we position this parking location on a sidewalk that have high widths in order to avoid blocking the right of way of pedestrians. This is the map for the parking location identified in high-use zones. If financial resources allow, we recommend the cities to add all the identified parking sites, the high, medium, and low demand. If municipalities face budgetary constraints, they can consider adding the low demand parking site just in case high or medium demand parking sites are not available within high-use zones. For example, let's take this high-use zone. We don't have any high demand parking or medium demand parking, so we advise city to add those two low demand parking in order to mitigate the cluttering issue of e-scooters. So this paper also seeks to identify high-use corridors using e-scooter trip data, and we compare various techniques used in prior study to identify corridors. E-scooter company in general provide cities with two types of data. The first one is data without trajectories, where just the origin and destination point are provided for each trip. In this case, two methods were proposed to estimate the path taken by each trip: the shortest path method and the case shortest path method. The second type of data is trip data with trajectory, where we have GPS point along the route taken by an e-scooter rider. So a method is developed to conjoin trip data, the trajectories, to street segments in order to identify which street were used by the rider, and in order to identify the high-use street corridors at the end. So let's elaborate more with the first two methods. For trip data without trajectories, they uses the following algorithm. This algorithm uses the shortest path algorithm using Dijkstra. So the developed algorithm enumerates in ascending order a set of paths between the origin and destination. And then it assigns for each trip either the shortest path, which is the first element in the path list, or the case shortest path having a travel time equal to the actual trip duration. So for this method, we developed a generalized cost function for the network links that estimate the time needed to cross the link while accounting for features such as user route preferences and the road characteristics. The following function is used to compute the time required to travel along link I, where Ti is the travel time assigned to link I in seconds, Li is the link length in meter, V scooter is the average scooter velocity in meter per second, Wi is a binary variable equal to 1 if link I crosses a traffic light and 0 otherwise, and T crossing the additional time for crossing a traffic light. And alpha is a reduction factor to account for the type of the infrastructure. Next, we have the method for data with trajectory. For the trip data with trajectory, where all the GPS points along a given route are provided, a simplified matching heuristic was developed to match the trip trajectory data to the street links. And not only this heuristic matches the GPS points to the network state, but also it finds past state when gap occurs. So when we have a gap, this heuristic can identify the street that any scooter rider used in order to continue his route to his destination. So for the simplified, the matching heuristic was inspired by the simple idea shown in this figure. This figure illustrates the method used to detect the link the GPS point lies on. So as shown in this link and this figure, a network link is represented by two nodes. We have the upstream node and the downstream node. In order to check if a GPS point lies on a link, we need to check that the distance from the upstream node to the GPS point A and the distance from the downstream node to the GPS point B is equal to the link length C. But due to the inaccuracies of GPS data, this method is further adjusted via the pseudocode presented here that was inspired by the triangle inequality theorem. So a comparison is also made between the list of high-use street links found by the shortest path and the case shortest path methods, and the list of high-use street link found by the simplified matching heuristic, which is assumed to identify 100% of the link at each rank. Overall, the results shown in Table 2 indicate that M2 performs slightly better at estimating street links than M1. And overall results show that shortest path models adopted by previous studies underperform when it comes to predicting the actual path taken by scooter users. Therefore, using actual GPS trajectory data is advised for capturing actual high-use road segments.
Sorry to interrupt. 2 minutes left. Just keep track of time.
Sorry. Do I continue?
Yes, please. Just keep that in mind.
So this map is a heat map of street links with high scooter trips. Also, these high use links are identified in the 3 areas of attraction the downtown, the uptown, and the entertainment district. And in this paper, we also discuss solutions that can be implemented in order to enhance micromobility services, such as adding painted corrals and bike rack at the identified parking locations. And at the high-use corridors identified, road infrastructure improvement can be added, such as the bike lanes. And furthermore, these corridors represent best location for ordinance enforcement. To sum up, this paper provides method for analyzing area of high parking demand, identify e-scooter vendors launching site, provide techniques for analyzing roadway segment of high micromobility demand, discusses policies, implication and potential environmental impacts, and examine the accuracy of shortest path model in predicting e-scooter passes. Thank you so much for your attention. I would be happy to answer any question.
Thank you so much, Myriam. Very interesting presentation. Does anyone have a question? I do have some questions. So you identified the corridors that are the highest demand for the electric scooters. I wonder if you at the current infrastructure level that you have, did you find out that there were mainly corridors that have bike lanes and sidewalks? Are you able to identify whether or not are they riding in the sidewalk or the bike lane?
Yeah, due to like the inaccuracy of the GPS data that were provided from the trip data set, it was hard for us to identify if the user is using like the street or the sidewalk, because they were really inaccurate. So also we advise like maybe to improve like the accuracy of this data in order like to identify where actually these riders are using their e-scooter.
Okay, but can you do you have like access to the current bike lane coverage in the area?
Yeah.
I wonder if those scooters were also in streets with high speed or low speed. Do you know?
They like the majority of trips, they use like the low speed routes, not the high speed streets. Yeah, we found out like they are using especially like the one that have like bike lanes and bike trails.
Yeah, yes, interesting. Anyone has questions for Myriam? Okay, so we'll continue with next presenter. Thank you so much, Myriam. Just for the others presentations, remember we have 50 minutes to present and 3 minutes for questions and answers. We're gonna present now understanding pedestrian accessibility, a scope and literature review. Presenter is Merlin from the Florida Atlantic University. Luis, please introduce yourself.
Sure. Let me see if I can get my share my slides first. Can you see my slide?
Yes.
Okay, great. Yes, my name's Merlin. I'm an associate professor at Florida Atlantic University. My co-authors Ulrike, Jehle at Technical University of Munich. And as Natalia mentioned, I'm going to present a literature review on walk accessibility today. Okay, let's see here. Okay, so first I want to talk about the approach or the methods for the literature review. This is probably the most important slide actually of the whole presentation, which is the decision to focus on walk accessibility as opposed to walkability. There's a very large literature on walkability out there. However, walkability is a very inclusive topic, very broad topic. And there's actually several different definitions of what walkability means. For example, the environments that see the most walking, or the environments that are enjoyable for walking. With this literature review, we decided to focus on the concept of accessibility. And that is a more narrowly defined concept focused on ease of access to destinations. And therefore, we had more focus in this literature review than if we had included all of walkability. And this leads to two of our key exclusion criteria for this review, which is one is that the paper has to consider walking to destinations of some kind, and the paper has to include some concept of impedance, distance, or cost. So this is what's called a scoping literature review. There are actually many different kinds of literature reviews. The purpose of the scoping literature review is to explore the outer boundaries of a field. So we didn't apply any quality criteria to the papers we reviewed. If it met our criteria in terms of relevance, even if it wasn't peer reviewed, we included it. The goal is really to explore the range of concepts that are being employed to understand walk accessibility. Get an idea of the boundaries of this field. So the search strategy is pretty straightforward. We're looking for one term related to pedestrians or walking, or it could even be non-motorized, and we're looking for a second term related to accessibility. We also tested the word access because that is sometimes starting to be used for accessibility, but we just found far too many results. We looked at 3 databases: Web of Science, Google Scholar, and the Transportation Research Board database. And after removing duplicates, we had a total of 175 papers that matched these terms. And then we went through paper screening. The paper had to be available in English. Not all of them were. The primary mode of travel had to be walking. It had to discuss walking to destinations, and it had to include, as I mentioned before, some measure of distance, time, cost, or impedance. After screening, we had 78 papers for the literature review. So something that was interesting, this is a map of the locations of all of our papers. You can see that there's quite a global interest in the concept of walk accessibility. We have every continent represented here except for Antarctica. And it's also interesting that it's quite interdisciplinary field. They're not just transportation, but GIS sciences have papers on walk accessibility, health, and just general urban planning. It's a very broadly, there's a lot of interest in this topic across the globe. So our analysis framework, how did we understand these papers? We looked at the 4 dimensions of accessibility as identified by Gers and Van Wee, which are the transportation dimension, the land use dimension, the individual dimension, and the temporal dimension. And we also added an analysis section on exactly how was impedance calculated for each paper. So now I'm going to go into a summary of our findings, and it's basically going to be organized just as I just discussed along these 4 dimensions plus impedance, so along these 5 dimensions, if you will. So first, just what transportation infrastructure? How do we measure it, and what does it include? It's not just sidewalks. There's also off-road paths, shared use paths, underpasses, overpasses, street crossings, stairways. And then there's literally dozens of variables that you can consider. Things such as the surface, the slope, the presence of obstacles, the presence of orientation features, the presence of benches. This is just a summary of the kinds of variables that are available for pedestrian infrastructure, but there are dozens of variables that you can gather that are relevant. Many more than there are that are relevant for streets, because pedestrians are influenced by micro-scale features of the built environment. Our general findings for the transportation dimension is that most of these studies, even though they studied pedestrian accessibility, they actually had a lack of adequately detailed data about the pedestrian network. In fact, the most common approach is just to use the roadway network and then to remove some links that are highways or limited access roadways and use that. And clearly that's not ideal for analyzing pedestrian accessibility. In a handful of cases, I'd say less than 10, researchers went to substantial trouble to construct extremely detailed pedestrian networks, including things like overpasses, underpasses, building entrances, and so forth. But that was, again, very rare. And then the pedestrian network itself actually interacts with the individual dimension. The pedestrian network and the data you need depends upon the user type. So if you're focused on wheelchair using persons, you actually need to gather somewhat different kinds of data or types of data. And walk accessibility, when you calculate it, it varies depending upon, unsurprisingly, depends upon the pedestrian network that's gathered. So gathering an accurate pedestrian network is important. Next, I want to discuss the land use dimension. Land use features in 3 different ways: the location of origins, the location of destinations, and is the built environment context along a given route. For origins, we saw residences used, particular individual buildings used, and in some cases, any possible location throughout the city used as a possible origin. Destinations are quite diverse in walk accessibility. It's not just jobs. People are looking at jobs, parks, healthcare facilities, schools, childcare facilities, shopping centers, and transit stops. And importantly, the surrounding land use can influence the level of experienced impedance. So for example, there's some evidence that people have a preference for walking along commercial streets, and it's perceived as actually being a shorter distance. Similarly, for walking along streets with greenery. The individual dimension, some of the variables that have been examined in terms of walk accessibility include age, gender, income, health, mobility constraints, vision constraints, and vehicle ownership. The most common demographic category analyzed, interestingly, is older adults. Sometimes adults 60 and over, 70 and over. Wheelchair users are also commonly analyzed. There are 2 very different approaches to analyzing the individual dimension. One is to look at groups of people, for example, older adults, people over 60, people over 70. The other approach is to create a fully individualized approach, which is to take into account multiple variables regarding a person, their age, their gender, their health, and to create a fully individualized accessibility measure for each person. So it's interesting to see that there's these 2 very different approaches. And socioeconomic variables are less often taken into account, but also have been considered in some of the literature. Relative to the other 3 dimensions, the temporal dimension is definitely the least studied dimension. However, we know that time is important in walking, in particular with regard to variations in weather, heat, cold, and rain, and lighting conditions necessary for nighttime travel. So just a couple of examples. Arith et al. Found that shaded and covered routes are preferred in hot, sunny Singapore. And they also found that covered routes increase in value or decrease in perceived distance during rainfall events. And Jehle calculated how accessibility varies over the hours of the day based on when different destinations are open. So this is a relatively understudied aspect of walk accessibility. The impedance dimension is quite complex for pedestrian accessibility. Normally, when we think about accessibility for vehicles or transit, we just look at travel time and cost. But for walk accessibility, there are so many more dimensions. Every one of these dimensions has multiple variables, as I mentioned, for transportation, for the individual, and for land use. Plus, there are actually interactions between these dimensions. There are individual dimensions that interact with transport dimensions, and there are individual dimensions that interact with land use dimensions. So calculating impedance is complex, and the methods for calculating it are quite varied. So lastly, I go into recommendations for research and practice. This is a very fruitful area for research because it's still an emerging field. These are somewhat simplified recommendations or stylized recommendations, but I just want to give you a flavor for the overview of what we found. Overwhelmingly, the current research into pedestrian accessibility uses the roadway network, but we recommend that actually specific pedestrian networks be constructed, including street crossings. So when you use the roadway network, you ignore the location of building entrances, you ignore the impedance caused by street crossing, and that's why a dedicated pedestrian network is needed to do an accurate calculation. Zones are quite often used as origins. Zones make sense as origins when you're studying auto or transit travel, but when you're studying pedestrian travel, the micro scale environment matters quite a bit. So where possible, we recommend actually using specific buildings as origins. That's increasingly possible with the computing power that's available today. It's still quite common to treat all persons the same. where this is clearly not the case with walking. We recommend that distinct population segments be used, such as older adults, children, people in wheelchairs. Overall, the temporal dimension has not been considered, but we do recommend considering especially the effects of weather and nighttime on walk accessibility. Those can both have a very strong effect. And interestingly, distance is most commonly used as our measure of impedance. And in other words, how far it is to get to something is the most commonly used measure. But there's some advantages to travel time. One advantage to travel time is that if people walk at different speeds, you can differentiate their ability to access destinations by taking into account those different speeds. You can also add in the time of a street crossing. So time is a more flexible dimension than distance. Now, time and distance are in some sense equivalent because you can convert them back and forth, but it seems a little bit more flexible to work with time rather than distance. So just a summary of our recommendations. Considering all of the variables that are available that can impact walk accessibility, we actually expect that a comprehensive measure that takes into account all of these variables is likely impossible to calibrate. We probably will never have enough data and enough walk trips observed to create a silver bullet model of pedestrian accessibility. Therefore, at the beginning of your walk accessibility project, you really need to be strategic. You have to think about, based on the literature, what are the variables that have the largest effect and are the most policy relevant? So there's some variables that have been ignored, as I've been mentioning before, things like weather, things like street crossings, that probably could add a lot to our understanding of walk accessibility. But you really have to be strategic at the beginning of your project. What are the variables you're going to gather and why? We do think it is possible to shift from roadway networks to pedestrian networks. Roadway networks is really a fallback option only, and especially with open street maps and more people gathering data on pedestrian networks, it should be feasible. It's possible for both researchers and practitioners to use actual pedestrian networks. One area we think that there's reason for focusing is on the quality of street crossings. That is something which we think has a significant effect depending on where you are in the world, and has largely been ignored. And then lastly, this is a bit of an opinion, but we recommend a population segment approach rather than the fully individualized approach. The fully individualized approach almost gives you too much information, and it's harder to make recommendations about what policy interventions are going to help certain populations of interest. So there's some academic interest in the fully individualized approach, but in general, we don't recommend that approach. So have some references here and have my contact information. I'm very interested if any of you are working on research on this topic on walk accessibility. Be very interested to hear what you're doing and what your approach is. Be happy to informally advise. I think this is a very interesting and promising topic for the future. Thank you.
Thank you so much. Very interesting work. Anyone has any question for Luis?
Yeah, thank you, Luis. I got a question about the pedestrian network you just mentioned. Yeah, first of all, thank you for that. Thank you for the pretty interesting presentation. So my question is about that. So you said we shifted from the road network to the pedestrian network, but the pedestrian network is pretty hard to define. I think the main reason is that pedestrians, it's not like vehicles we can regulate and just drive inside the lane, but pedestrians actually works everywhere. Like they can actually use the road networks as the walkway, and so if we want to shift to that pedestrian network, how do we resolve such challenges?
Yeah, I mean, in most cases, there is a pretty well-defined pedestrian network in terms of sidewalks, off-street paths, street crossings, underpasses, overpasses, building entrances. There are places like college campuses where people walk in every direction, right? And you can kind of, I think, observe where people are walking and add some links to represent those kind of cut-through paths, those cow paths, if you will. There is some research on on calculating walk accessibility that uses not a network, but uses a rasterized method. In other words, you are allowed to walk anywhere. So it's like point by point. And based on things like terrain and slope, walk accessibility can vary. But the disadvantage of that method is that it's very computationally expensive. So I would recommend that in most situations, you build a pedestrian network, even if it's not perfect, that's simulates the paths that are most often taken.
Yeah, thank you very much. That's pretty good.
Thank you. I do have a question. So you mentioned about the network availability, but maybe thinking a little bit more on the demand side with the literature review that you did. I wonder how openly available are pedestrian count data. I think that has been one of the main issues we have had in the past when we do this type of research, that at large scale, there's not actually information of walk miles travel at the state level, let's say, or pedestrian counts that are not focused on one intersection or one segment. So did you find out how much accessibility is there for pedestrian counts and in general walk miles traveled?
No, that's a really good question. The pedestrian travel behavior is hard to study. It's part of our overall household travel surveys, but it's only a small percentage of those trips. That's another area where data is lacking. These studies were focused on measuring pedestrian accessibility, which actually you don't have to observe people walking, you just have to measure the built environment, and based on existing research or your own research, try to calculate what is the effect of that built environment on the ability of people to reach destinations.
Yeah, understand. It is very difficult on the demand side to get that information with the supply side, because at the end, if you make any change that make more accessible, it will be also very interesting to see how much the demand would have been increased.
Yeah, you can put pedestrian counters in place. I mean, they do exist, pedestrian counters, and you can study them longitudinally. I mean, that's what I would recommend, is you put a couple of pedestrian counters in place and study it longitudinally. But yeah, in general, there's not good data on pedestrian travel behavior, including pedestrian routes
mainly localized, no? Because like at large scale, it's when there's very, very lack of this type of information. But then very thank you so much for the presentation. Vince, you raise your hand.
Yeah, I had a question. Can you comment at all about what you saw in terms of different distance decay functions or impedance decay functions in the accessibilities?
Yeah, I mean, there are a couple of papers that study different functional forms and different distance decay functions. I have a different paper that finds that people walk significantly further in Germany than they do in the United States. Germany and the United States have very similar travel behavior surveys, so the data is quite comparable. I think it does vary. It does vary, and that's kind of implicit in our measures of accessibility is what individual factors, what built environment factors, what transportation factors are going to make people want to walk further or want to discourage them or create a disincentive to walking. That's kind of what we're trying to measure when we measure walk accessibility.
Thank you so much. We're going to continue with the next presentation. It's congestion and environmental impacts of short-car trips replacement with micromobility modes by Zhufeng from Carnegie Mellon University. Zhufeng.
Sure. Let me share my screen.
Thank you so much.
Yeah, hello everyone. My name is Zhufeng. I'm a PhD student from Carnegie Mellon University and also a micromobility enthusiast. Today I'm going to present my work that is the congestion and environmental impacts of replacing short car trips with micromobility. Nowadays, as we know, traffic congestion has become one of the biggest challenges in global cities. Currently in the US, half of the trips are short trips, meaning less than 3 miles, but only 2% of short trips are done by bicycles, whereas 50% are made by privately owned vehicles. So therefore, micromobility may represent a significant opportunity to replace short private vehicles because bikes use far less space than cars on the street. Micromobility, defined as bikes, e-bikes, scooters, e-scooters, is pretty suitable for replacement for short car trips. First, it can serve as a similar purpose as cars for shopping and commuting as daily use, and it's already integrated with some other modes such as public transits. And it can achieve a very similar speed in congested urban corridors. So it can become more active and mature short distance transport alternative to private vehicles and could help us resolve the city congestion problems. And in this research, we answered two main questions. First is, what is the upper bound potential for micromobility to replace short car trips? And second is, what are the resulting impacts to congestion and energy use and emissions from the mode replacement strategy? We answered the two questions by performing a case study in Seattle, because Seattle is one of the cities with the greatest potential for micromobility usage, as short car trips account for a half during PM peak hours, and Seattle is investing a lot of money for its bike infrastructure to encourage micromobility usage. And the whole study area covers the whole Puget Sound region. It's a whole Seattle metropolitan, and Seattle is the target area, which is for us to conduct analysis, traffic analysis. And we also include other counties surrounding in order to capture all the trips that start from and end in the city of Seattle to generate a more comprehensive traffic analysis result. We use the PSRC, that is a Puget Sound Region Council household survey data and weather data to estimate the upper bound potential for replacement. The potentially available trips that can be replaced are short trips made by private vehicles occurring in PM peak hours. And these trips have to satisfy some conditions to be replaced. First, we define a tour that is a combination of several trips that starts from a person's home and returns to his home. If all of the trips within a tour are less than 3 miles, and none of the tours within a tour is shopping or picking up someone, and the commuter age is older than 16 years old, and all of the trips did not occur in inclement weather condition, we assume that all the trips in this tour can be replaced. And we apply this filtering process at different regions in the city of Seattle, because trip information is different across different regions, and downtown area may have higher potential for micromobility to replace short car trips. And on average, the upper bound potential, as we estimated, is about 18% in the city of Seattle. After getting the replacement rate, we perform traffic simulation models to compare a normal case with some cases where some trips are replaced. The traffic simulation is conducted using the planning software called Vism. The first step is to reproduce the 2014 traffic condition using PSRC's travel demand model. A static traffic assignment is made to allocate traffic volumes that start from or end in the traffic analysis zones. We calibrate the model by using the T-fuzzy function to adjust the demand matrix in order to match the observed traffic counts on street segments with the simulation values. And as we can see, in terms of all the metrics we are using, the baseline model is able to reproduce the traffic volume in Seattle. And mode substitution is done with the demand matrix. Demand is an OD matrix, which details the number of trips by different modes for each TAZ origination destination pair. And for each origination destination whose traveling distance are short, we consider the following cases for replacement. So if there exists a designated or protected bike-lane route between origination and destination, we assume that bike trips would not affect private vehicle traffic stream on vehicular roads and remove all the trips from the trip table. So if there is no designated bike lane, but there exists a route between origination and destination, and bikes are allowed to share roads with cars, the replaced short vehicle trips will be converted to 0.5 passenger car equivalent following the highway capacity manual, and micromobility trips are simulated as cars in the model. And if there is no possible cycling route in the road network between origination and destination, we assume that the short vehicle trips cannot be replaced by micromobility, and as a result, no changes are made to the origination and destination matrix. By comparing results from every traffic simulation scenarios, we can observe that mode replacement can help alleviate traffic congestion issue. And we use the ratio of simulation speed versus free flow speed as the congestion evaluation metric. Travel speed increases as micromobility penetration rate increases, and especially at the most congested areas, such as a stop sign, yield sign, like a traffic light in urban corridors. Because these areas are more sensitive to volume delay functions we used in the traffic simulation model, and more significant impacts can be observed when bike lanes are widespread all over the city, meaning the first replacement case happens all the way in the city of Seattle, and in this case, we can maximize the benefit from the replacement strategy. And this map can be translated to a bar chart. It shows the percentage change of the number of road segments under different congestion levels. The orange bar is the case that we assume there always exists a protected bike line between origination and destination. And gray bar is the 2014 bike lane deployment where we use for our baseline model. At the upper bound potential, number of severely congested roads decreased about 10%. And if bike lanes are widespread deployed, as the orange bar shows, the improvement can be much more significant. So even if we can see a significant impacts in terms of traffic congestion, the environmental impacts are disproportionately low, as we can see from the table. At the upper bound replacement rate, 8% of total trips are replaced, but only 2% of the emissions and energy use are saved. This is because micromobility is not a carbon neutral mode. And given that the replaced trips are short, and short trips will not produce too much emissions. So in conclusion, in this research, we first estimated the potential for micromobility to replace short car trips during PM peak hours. And the average in Seattle, the upper bound is 18%. And we can observe the significant congestion reduction, and bike lanes are needed to realize full benefits of micromobility replacement. And because short trips account for disproportionately low amount of emissions and energy use, in addition to micromobility usage, some other strategies such as car and truck electrification are needed to meet the climate change target, and in order to reduce transportation sector emissions. And don't hesitate. This paper is published in literature, and don't hesitate to check that. And thank you for listening. Don't hesitate to give me any questions. Thank you very much.
Thank you so much for the presentation. Very interesting work. Does anyone have a question for Zhufeng?
Sure.
Luis has his hand. Can you?
Can you hear me?
Yes.
I can hear you.
Yes.
Yes. Very interesting study. I really like what you've done. I do have a question though. Did you consider you didn't consider travel age. You considered at least 16, but did you consider a maximum age? Because micromobility definitely skews towards younger people.
Yeah. So in this case, I think we normally consider the shared bikes, and most of the shared bike companies only allow users older than 16 years old to use their service. So our upper bound estimate is a filtering process, and if the commuter age from the trip table is younger than 16 years old, we don't allow them to use the micromobility because they are not allowed to use.
Yes, I understand this. What I would this is just a suggestion.
Okay.
Consider not including people over 50.
Okay.
Older, there's not a lot of evidence that older adults are using these in large numbers. So you might have a maximum age as well.
Yeah. It makes sense. It makes sense. We tested from empirical statistics, and some like elder population did not use micromobility that much, but the companies don't have upper cutoff age for the elder people to the senior people to use the micromobility. So we didn't perform the upper bound to prevent them using micromobility. So the threshold is older than 16 years old. But thank you for your suggestion.
Thank you so much. Thank you. It's an interesting question because, as he mentioned, there's not for considering replacing short trips. The population description is very. The population who uses electric scooters, who tend to use electric scooters, is kind of more unique in that sense. But I think the work is very, very interesting. Thank you so much for your presentation.
Thanks.
So our last presentation is how do street attributes affect willingness to walk? A citywide pedestrian route choice analysis using big data from Boston and San Francisco by Rounaq Basu from Massachusetts Institute of Technology. Rounaq, please introduce yourself and share your slides. Are you able to share?
Can everyone hear me?
Yes.
Okay, great. Can you see the slides?
Perfect.
Okay, excellent. All right, so
maybe, sorry, you can do the, okay, yeah, perfect. Now presentation mode.
Yeah.
You good?
Is this fine?
Yes, fine.
All right. So yeah, good morning, afternoon, evening, and night for everyone who's joining us. I'm very excited to be here at the 4th BTR conference, keeping my streak going of presenting at this conference over the last few years. And today I'll be presenting some work Andres Sevtsuk and I have been doing here at MIT on understanding pedestrian route choice using some big data sources. Yeah, so the outline of this talk is pretty straightforward. I'll try to motivate you about why it's important to look into pedestrians, not that you need much motivation given the talks that we've just heard. Talk a little bit about the literature on pedestrian route choice and how we try to contribute to that literature, and then dive into the specifics of the couple of studies that I'll be highlighting here. So talking about the research methods, results, and then providing some key takeaways from our work in Boston and San Francisco. So yeah, there's been a long history, as we all know, of auto-oriented development. We've been unfortunately guilty of designing cities that favor auto dependence, and there's been a lot of funding, not just for that sort of design and infrastructure, but also around modeling. So we know that auto-oriented travel demand modeling has been funded inordinately. For example, the 4-step model, which we are all aware of, shortchanges active mobility. So the focus is entirely on auto trips, and at the end, we just get the mode share for active mobility, and we don't even care a lot about assigning those trips, at least along the pedestrian network. And we obviously have a lot of evidence that poor design for pedestrians has caused accidents, injuries, and deaths. So why should we care about pedestrians? Very simply, because most of us are pedestrians. We travel a lot. Most of our trips are by walking. And the benefits, if we really care about, start to think about pedestrians from an economics perspective. So what would be the benefits of a more pedestrian-oriented outlook? well, we would be reducing auto dependence, obviously, and that translates to reducing emissions. Walking more could have public health benefits, and there's a whole other host of benefits. So moving on to, I'm not sure if there's some background noise coming from someone, but yeah, I'll plow ahead. So the second section talks about paths and preferences. So what do we know from the literature about pedestrian route choice behavior? So what are the different variables that influence the different kinds of routes that pedestrians take when they travel around the city? So one is obviously the convenience that pedestrians associate with walking around. So the presence of a sidewalk, the average width of the sidewalk, pedestrian density and flow, the number of turns they have to take, and the climate all influence what we're calling as pedestrian convenience. Then you have infrastructural variables which try to account for interactions between pedestrians and autos. So you have road crossings, ascending steps, crosswalks and overpasses, and then sidewalks right next to major roads where there could be like high traffic volumes or vehicles at high speeds, and that those could serve as impediments to pedestrians choosing certain those kinds of routes. Then you have the experience along the route, which could make certain routes more interesting. For example, you could have lots of amenities and storefronts. Pedestrians could have access to greenery. They could use those routes to get to transit stations, or there could be interesting public places along those routes, such as artworks or fountains or monuments and so on. And this is not as much of something that the literature is focused on in one particular area, but then if you start to make comparisons across areas, then terrain can matter, especially comparing across cities with very different elevations along the routes. And this can be interacted with climate, where pedestrians would be less likely to walk or travel shorter distances in places with hot climates. And then we have subjective factors. So all of these variables that I was just describing are objective factors, which we can measure using, let's say, route audits. But if we were to measure pedestrian perceptions of certain routes, then we'd need to go out into the field and conduct surveys regarding how they feel about the crime safety, the comfort, the familiarity with along certain routes and neighborhoods, or the noise. So what's the research gap over here? Prior studies, as the ones I just discussed, have been based on limited data. And how so? Well, they're focused mostly on niche samples, focusing on a very limited definition of study area. For example, folks have looked at places around transit stations, or focused only on the downtown area. And these data, because of funding issues and data collection issues, were collected only over a few weeks. So we don't have good continuous data that stretches out over multiple months or years, where we can try to look at seasonality effects. And because of all of these different obstacles, these sample sizes have been quite limited compared to some of the other route choice modeling efforts focused around automobiles, for example. And across these different studies that we've been looking at in the literature, what we've found is there are vast differences in data collection techniques and modeling frameworks, and these differences do not allow us to compare results across different cities, and that's really important for policymaking. So what are our research objectives? We're trying to use GPS traces of pedestrian trajectories to infer route choice, and the key component here is that we're trying to do this at scale, and I'll get to what that means in just a bit. We're going to use street attributes and try to estimate how those affect pedestrian route choice preferences, and operationalize these effects as willingness to walk measures. And I'll explain that as well. And then I'm going to compare effects between the two cities, Boston and San Francisco. And this is more reliable than what others have been doing, because we're trying to use the same data source and modeling framework. So what's new here? The bit about trying to do this at scale. So we're trying to do this at scale on 3 counts. First, spatially, we have data that covers the entire city, not just particular neighborhoods. Our data also cover a large period, almost a year, not just a few weeks. And our sample size is over 10,000 observations. And that's after cleaning. We initially started off with much larger samples. So this may not really seem big in the era of big data, but a sample at this scale is unprecedented for pedestrian route choice studies. So diving right into the research methods, as I've said, we've looked at two different study areas, San Francisco and Boston, and we have between 10,000 and 15,000 unique pedestrian trajectory observations. And as you can see, they cover the city. They're quite representative of walking around the city. So these GPS traces were sourced from a smartphone app, and the data cover years worth of time from May 2014 to 15. We match these traces to street center lines. And although our initial sample was over 100,000 observations, then we used various filtering methods and cleaning techniques to obtain what's called a usable sample for model estimation. That's, as you saw, between 10,000 and 15,000 observations. But obviously, these data are not without their limitations. Because we're using data sourced from a smartphone app, then there obviously is a sampling bias where we have data on their smartphone users, and more particularly people who've been tracked by that app, so to speak. And there's also this bit around anonymization. When we entered into the agreement to access these data, they were anonymized, so we do not have any information on social demographics and trip purpose, which makes it difficult for us to do within group comparisons across different subpopulations or across different trip purposes. So moving on to the modeling framework, we constructed a choice set, as the modelers here know. So we have the observed trajectories, which are the observed routes, and you need to construct a choice set of different alternatives. So we did that, and the choice set had at least up to 3 alternatives and at least 1 for each route. We used some filtering techniques to narrow the choice set down to this number. And what we found was we had every route had at least 1 alternative for both Boston and San Francisco. And we had over 50% of the routes with at least 2 alternatives, and many of them had 3 as well. So the independent variables comprise the usual suspects, which are drawn from the literature. So you have route length, turns, elevation, amenities, sidewalk width, and some auto interaction variables. We looked at highway exposure, traffic speed, and traffic volume. And we added in a couple of computationally intensive so-called modern additions, because these could not be measured back in the day. And these the measurement of these 2 variables, which are exposure to the open airs, which we're calling the sky view factor, how much of the sky can you view along the route, and the green view index, how much greenery is there along the route. So we used Google Street View to infer these variables. And as you can see, just an example of what we did. So we looked at the Google Street View images, did some image processing with machine learning techniques. We don't need to get into the details of that right now. And then we computed what % of the route covers access to greenery or access to the sky. Just as an example, for those of you who are familiar with San Francisco, you can see the spatial distribution of the green view index over here. So Golden Gate Park, Presidio, Lake Merced Park, they all have very high green view values, and downtown has comparatively lower green view values. In terms of the model, we use the path size logit model, which is fairly well known and well suited for these sorts of applications. And the main difference here between the path size logit, which is the PSL, and the multinomial logit, which is the much more common and the more traditional model that all of us probably are familiar with, is that there's this additional path size factor that tries to account for the overlap between alternatives. And this factor is, or this correction is really useful when we try to model route choice, because many routes have some overlapping segments throughout the trajectory. So when we started to look at pedestrian route choice preferences, we looked at the different variables that I listed out, and we compared results across cities. Now, we can't really do an apples to apples comparison of the estimated raw effects. So right now we'll just look at the direction of those effects, whether they're positive or negative, and then we'll try to get into the comparison in just a bit. So route length obviously is expected to have a negative effect on pedestrian route choice, and we confirm that for both cities. Then looking at the number of turns, that it might look like it has a stronger negative effect, but that's not really the way to measure it, because raw effects can't be compared directly. We need to look at some ratio-based measurements, which I'll get to in my next section. So, but number of turns, again, importantly, has a negative effect on pedestrian route choice. Boston isn't really that elevated, and it's pretty uniform throughout. San Francisco shows a negative elevation effect for route choice as well. For sidewalk width, the variable for Boston wasn't statistically significant, but San Francisco showed a positive effect. So the more you improve sidewalk width, you should expect to see an improvement in the likelihood of choosing that route among pedestrians. Amenities, so exposure to amenities along the route also had positive effects, and this was true for both Boston and San Francisco. Now, this is really interesting. When we started to look at exposure to the open air through the sky view factor, we see some mixed effects. So in Boston, exposure to the open air or the sky is preferred for pedestrians, whereas in San Francisco, that acts as an impediment. The green view index, unfortunately, wasn't statistically significant in either city. Neither was exposure to highway, traffic speed, and traffic volume. Both had negative effects as expected, because pedestrians feel less safe along routes that are next to major arterials. And the path size factor is expected to be positive based on the literature, and we just confirmed that it's positive for both cities. So to summarize, we found that the route length, the number of turns along a route, elevation, and exposure to the highways or autos in general, as measured through speed or volume as well, have negative effects. And in terms of positive effects from a more policy-oriented perspective, so we can certainly think about improving sidewalk width, improving the streetscape by adding in more amenities and street front establishments, and exposure to greenery. And open air exposure was found to have mixed effects. So it was positive in Boston and negative in San Francisco. So how do we operationalize these as willingness to walk? So as I mentioned, we can't really compare those raw effects across cities, but what we can do is compare ratios. And when we start to do that, many of us might be familiar with this metric, which is known as the value of travel time. So what we do is we take the ratio of the coefficient of travel time and the coefficient of cost, and that gives us an estimate in dollars per minute. Similar to that, we constructed this measure that we are calling equivalent walking distance. And we use the coefficient of the route length as the denominator, and we can use the coefficient of any other street attribute variable in the numerator, and that'll give us the number of meters per turn or per amenity or per 1,000 vehicles in terms of traffic volume and so on. So if the value of travel time were to be 0.25, then we would interpret that as individuals being willing to pay 25 cents more to reduce travel time by 1 minute. So the willingness to pay would be 25 cents per minute. Similarly, if the equivalent walking distance for turns were to be 25 meters, then we would interpret that as individuals being willing to walk 25 extra meters to avoid one turn, and that would be the willingness to walk. So if we were to increase the number of turns, as you can see over here, so I've listed out some of the key policy variables and increased all of them. So if we were to increase the number of turns by 1 along the route on average, the willingness to walk would decrease because we've made the path more onerous for pedestrians, and pedestrians, as we saw, don't like too many turns on their routes, and these effects are different across the two cities. For sidewalk width, increasing the sidewalk width would have benefits in terms of increasing willingness to walk in San Francisco, but not in Boston. Amenities have a positive effect on willingness to walk in both cities. The sky view factor, as we saw earlier, has mixed effects. The green view index, unfortunately, still remains statistically insignificant. For traffic speed and traffic volume, we found that San Francisco is much more sensitive. Pedestrians in San Francisco are much more sensitive to these auto-related variables along their routes. So to summarize, the key policy variables that emerge from this analysis would be, in terms of designing the built environment, would be turns and sidewalk width. So one extra turn reduces willingness to walk by 30 meters in Boston and around 60 meters in San Francisco. And at the same time, increasing sidewalk width by 10 feet on average along the route increases willingness to walk by 80 meters in San Francisco. And we found that pedestrians in San Francisco are much more sensitive to auto traffic than in Boston. So how do we start to translate these into policy recommendations? Well, we looked at pedestrian accessibility, and this builds off of some of what Louis was presenting earlier. So one of the most popular and easy to operationalize measures of accessibility is the cumulative opportunities measure. What that tries to do is provide an estimate of the number of opportunities that can be accessed from a location within a given travel impedance threshold. And that impedance could be defined through distance, time, or cost. And we can use this to construct catchment areas, which, for example, could be walk sheds around transit stations. So when we think about routing options, obviously you have you could make choices along what network you want to use, as well as the mode you want to use. For this analysis, we are obviously going to stick to pedestrians. But when we think about routing options, then we could be looking at the Euclidean distance. So you start off at a point and you assume some Euclidean distance, which could be, let's say, 1 kilometer. And because it's Euclidean distance, it's going to be uniform in all directions. And what you end up with is a circular catchment. But instead of Euclidean distance, if you were to use network distance, then the distances along different directions wouldn't be uniform, and you'd end up with very non-uniform catchment area or walkshed that would have these jagged edges. But both of these
sorry, Rounaq, we're almost on the time, so just
I'll wrap up. So thanks. So in terms of operationalizing these, so Euclidean and network distance catchments have been used and are being used, but what's not being used is perceived distance. So can we use the route choice preferences that we just analyzed and plug that into this accessibility analysis so we can get perceived distance along the network instead of objective distance that does not account for what's happening along the route? And we did that both for the BART system in San Francisco, where we found that the perceived accessibility is 30% that of objective accessibility in areas outside of downtown. It's better in downtown. And in Boston, we looked at the MBT and we found that it's less than 50% of objective accessibility. So to summarize, in these two studies, we tried to improve on the scale of pedestrian data, both in terms of the spatial, temporal, and sample size representation. And these willingness to walk measures can help planning practitioners improve urban design oriented around pedestrians, prioritize which particular variables need to be looked at for infrastructure improvements, calculate more realistic pedestrian accessibility to transit, and compare walkability across cities. But obviously, limitations remain when we use big data sources. For example, we could not compare across socioeconomic groups, which means that we need to supplement these types of sources with targeted surveys of underrepresented groups. Both of these papers are published. One of them got this award from Travel Behavior and Society, so you're free to read them up. And with that, I'll open the floor up for questions, and thanks for your attention.
Thank you so much, Rounaq. Very interesting work. We have some questions in the chat by Louis. So the first one is, how do you define and count amenities?
So we looked at different establishments along the route and just counted them up. And these data are available from any form of like business databases, for example, Esri Business Analyst.
Thank you. And the next question is, do you have any reason why pedestrians in San Francisco would be more sensitive to traffic?
Yeah, we thought a lot about that, and it may boil down to a measurement issue. So in Boston, throughout the city, there are very strict speed limit laws. And because of that, we didn't observe a lot of variation in our route data across the traffic speed and traffic volume variables, which is why that lack of variation could have led to the variable being, or the effects being, statistically insignificant.
Okay, thank you. And then Vince is asking, did you consider the number of street crossings?
No, we did not. So yeah, building off of Louis's earlier recommendations, that's something that's definitely worth looking into. We have efforts going on where we're trying to create pedestrian street networks using satellite imagery. We did augment the street network from the Tiger Line shape files with some data from OSM as well, but because this is historical data, it's a challenge to maintain temporal consistency.
Thank you. So another question from Beans. What was the smartphone app for which the data was sourced, if you can say?
We are not authorized to share that, unfortunately, but it doesn't exist anymore. It's not Strava. It was acquired afterwards by another company, which is why we were able to get access to that data.
I see, understand. And then Shirley is asking, since it's big data, have you considered machine learning in your analysis?
We have not. So the goal here was to understand behavior preferences, and econometrics has provided us with a rich toolkit to do that already. So we haven't really looked at machine learning techniques to do the same thing, but there are emerging methods from what I hear to do that. So that could be something to consider in the future.
Thank you so much. Anyone else have any other question that you want to share with Rounaq? If not, thank you so much, Rounaq, for the presentation. Thank you so much for the other. Oh, sorry. There's one question from Sarason from Fell Highway. Did you consider land use data?
What kind of land use data? Like just the zoning?
Sarah, do you want to elaborate? Yeah, could be the zoning, but like maybe commercial, not commercial. What
Yeah, I'm not sure if pedestrian route choice would depend on zoning. So a way to account for that is to look at amenities. So obviously residential neighborhoods are going to have fewer amenities along those routes. And that's what we try to capture. And commercial neighborhoods would have much more, but I'm not sure pedestrians would look at zoning.
It might be related to attraction, no? Because many pedestrians are more attracted to commercial areas than residential areas. Just if you live there, you go there. But if there's a commercial area, it's probably higher volume. So it's probably related.
That would be, I think, more about destination choice than route choice.
Got it. Yeah. So sorry, suggesting that could land use plans, census data, and any other overlay of this type of data could be useful for the analysis.
Yeah, that's a good point about census data. So we did think about trying to merge this data set with census data, but the fact is we don't have any information on who these pedestrians are. And just because the trip originates from a certain census tract, for example, does not mean they live in that census tract. So we can't conflate that the origin is their home zone or home tract.
Have you considered a follow-up with a survey more oriented towards personal characteristics?
Yeah, I think from these two studies, because we looked at a year's worth of data, which is arguably like trying to give us a more general sense of pedestrian route choice behavior rather than a more specific population cohort. So following this up with surveys targeted towards like subpopulations is something we are considering doing. So we would have access to not just socio-demographic information, but we can also compare across groups.
That would be interesting. Any other question to Rounaq or any of the other presenters? Feel free to do so.
Rounaq, I have a question.
Yeah,
and maybe, and this might not be a question you want to answer. That's okay. But how are you going to continue this research, since it seems to rely on these often proprietary data sets?
Yeah, I don't think we're planning on, because we don't have access to any other similar data sources. So I think this will be the end of big data analysis on pedestrian route choice for us for the moment. But then the insights that we did gain from these data sets are helpful for let's say when we do a survey later on, when we start to compare what we find from those surveys across socio-demographic groups, then we can try to like compare those estimates, again, this estimate and see, these estimates from the smartphone app and see like what's different, what's similar. So can we really claim that smartphone apps are giving us a general estimate of population behavior?
It's very interesting. It's a very interesting result.
Thank you.
Thank you so much, and thank you everyone for a very interesting research you're doing in micromobility and pedestrian. Any question, feel free to reach out to the presenters or to me, follow up. Thank you so much for attending the BTR. Hope to see you next year here. Good rest of the day and good weekend to everyone.
Thank you, everyone.